This is the Chapter 4 summary for the Deep Learning book, authored by Ian Goodfellow and others as presented on screen here. In this video I'm starting off on Chapter 4 of the Deep Learning book. This chapter is titled Numerical Computations. It broadly encapsulates methods and ideas related to solving mathematical problems by iteratively updating solution estimates to yield better answers, as opposed to analytically deriving a formula providing a symbolic expression for the correct solution. This type of iterative optimization method is very commonly applied in machine learning algorithms. For a variety of reasons, getting computers to properly carry out some computations can be difficult, and efficiency is a big consideration as well in developing these methods. So overflow and underflow in computer science is the problem of numbers being too large or small for a computer to handle them properly. This can happen because real numbers can theoretically have infinitely many digits, but need to be stored finitely on a computer. So for almost all real numbers, there's going to be some approximation error in representing them on a computer. This becomes rounding error, which can be problematic if it accumulates across many operations. Enough rounding error can cause algorithms that work in theory to fail. For example, when underflow occurs, a value may be rounded to 0. The difference between 0 and a very small number can be huge in carrying out operations. For example, the logarithm of 0 is negative infinity, and division by 0 is not possible. Whereas, for each of those kinds of functions, if you input, for example, 0.0001, you would have some actual value instead of infinity. The authors provide an example of this happening using the softmax function. I'll just mention that since it was new to me. The softmax function is used in a variety of machine learning applications. It takes in a vector, perhaps the output of some learning network, and maps it to a new vector in which each value is probability based on the magnitude of the element of the input vector relative to the other elements. So the larger the element in the input vector, the greater the probability assigned to it, and the sum of all probabilities in the output vector will add to 1. Naturally, underflow could cause a problem with that kind of computation, as the denominator could become negative infinity. Thankfully, we can usually rely on the foundational code of the programs being used to make learning systems to perform the stabilization of functions for us. Conditioning refers to how rapidly a function changes with respect to small changes in its inputs. Poorly conditioned functions represent a problem because rounding errors in the input could cause large changes in the output. In the case of the matrix inversion, the condition number is the ratio between the largest and smallest eigenvalues. So in the application of a poorly conditioned function, pre-existing errors that are present from having computed the matrix A are amplified, in addition to new error that might be introduced in the process of actually computing the inverse itself. Most deep learning algorithms involve optimization of some sort, and FYI, the optimization problem is usually framed as a minimization problem. The function being optimized is called the objective function or criterion, with some other names used when it's a minimization function in particular. Gradient descent is the name of a technique of using the derivative of a function to note the slope at a given point, and using that information about the slope so as to move in the desired direction for optimization, whether minimum or maximum. When the gradient is 0, it doesn't give any information about which direction to move. These points where the gradient is 0 are called critical points or stationary points. If a critical point has some neighboring points that are lower and some that are higher, then it's called a saddle point. On the left here is a simple example of a local minima and maxima in 2D, and on the right is a classic example of a saddle point in 3D. Minima or maxima are local as opposed to global when they are lower or higher only than any other points immediately around them. If the point is lower or higher than any other point anywhere on the surface, then it's the global minimum or maximum. One ever-present problem when trying to optimize is the problem of a searching procedure getting stuck in a local minimum or maximum and not being able to proceed to seek the true optimum, which is the global minimum or maximum value. But it should also be noted that if there are multiple points with the same optimum values, then all of those points can be global optimums. There can be multiple global optimums. It should also be noted that these types of points also exist for multi-dimensional functions, which might be impossible to visualize. Finding the true global optimum can be difficult for functions with many variables, so we can usually settle for a near optimal solution. We can't tell if a given solution is near the optimal, so we can just settle for something sufficiently good. Also, it should be noted that for the concept of minimization or maximization to make sense, the function being optimized must yield a single scalar output. If a function has multiple outputs, there just isn't a way to optimize it, since some level of subjectivity has to come in to be able to add some trade-off criteria between the two outcomes. For the same reason, the output must be a scalar, because if it was a vector output, then the concept of the optimum doesn't inherently exist with respect to vector direction. This chart from the text shows how there can be both insignificant and significant differences between local and global maxima, which is important to consider in determining when to stop an optimization procedure. What we learn in high school is the derivative, which is the rate of change of a function according to its input. For a function with multiple inputs, the partial derivative can be taken. It's the rate of change of that function if only one of its inputs is adjusted. The gradient operator denotes the gradient of a function, which is a vector containing the partial derivatives associated with all of its arguments. The critical point of a multidimensional function is the point where all of its partial derivatives are equal to 0. So of course, while partial derivatives are useful to determine how the function will change, if you travel only along one dimension, that's very limited. After all, on a multidimensional contour, who's to say that the direction which most rapidly optimizes will coincidentally be along only one of the major coordinate axes? To determine what the rate of change of a function is in an arbitrary vector direction, we use the directional derivative. The directional derivative can be computed as the dot product of a vector with the gradient of the function. Keep in mind that the vector has as many dimensions as there are inputs. So for example, when we think of a 3D contour, really that's a two-dimensional function where we use the third dimension to show the function output. At this point, I really recommend watching some videos that have great visualizations and illustrations of these concepts by Khan Academy. I'm sharing the link in the description. I find the best way to understand this is to think about the gradient as representing a vector. What you see on the left is how, if you think of the gradient as representing a vector, it's made up of components along each axis of the function. Its direction is then determined by the ratio between the partial derivatives of the function with respect to the different axes. What's critical to remember is that because this vector forms a right-angled triangle if broken up into its components, the vector, as the hypotenuse of the triangle, is the longest side. Building on this, because the derivative occurs at a point, and the function is known to be smooth and continuous, we know that if we consider the gradient in different directions, it would change smoothly, not abruptly. The implication is that, being the combination of both partial derivatives, the gradient actually represents the direction where the function changes most rapidly, that is, the slope is greatest. This is a really important point to understand and remember, and I'll try and make it clear in a couple of ways. First of all, getting back to the definition of the directional derivative, we said it was defined as the dot product of a vector indicating direction with the gradient. This can be interpreted as projecting the derivative onto the direction, or the direction onto the derivative, whichever you prefer. From the principles of the dot product, it should be well understood that a dot product is maximized when two vectors are collinear. Therefore, it follows that the directional derivative is maximized when the direction of interest is the same direction that the gradient vector makes. I'll reiterate these 2 points. The gradient of a function, interpreted as a vector, naturally points in the direction of steepest ascent, since the sum of multiple component parts is greater than any one part. Since the directional derivative is computed by projecting onto that vector, the directional derivative is greatest when the direction of interest is the exact same direction as the gradient. It should be understood that this is true regardless of the sign of the gradient. For example, the partial derivative is meant to indicate the change in a function as an infinitesimal step is taken in the positive direction of a given axis. But even if the partial derivative, and thus the component of the gradient, happens to be negative when that positive step is taken, the gradient still yields the direction of steepest ascent. That's because if the gradient is negative in the positive step direction, then its interpretation as a negative vector actually has it point in the exact opposite direction, which is in fact upward, the steepest direction. As was mentioned earlier, optimization problems are usually framed as minimization problems. In those cases, the negative of the gradient then provides the direction of steepest descent, the optimal path to take for minimization. While the gradient provides a direction in which to head, it doesn't provide how far to step in that direction. The equation here presents the natural model to follow. Given a current point, the updated point for testing will be the current point less some step size in the direction of the gradient for a minimization objective. The size of that step is called the learning rate. Different strategies can be used to optimize how to use this method. Most simply, you could use a constant value step size and keep iterating. Line search is the idea to test steps of multiple sizes in the direction of the gradient and select the step size yielding the optimum outcome. This can slow down the total iteration time by skipping over redundant steps where the optimal direction is the same. It also carries the risk of skipping over relevant portions of a multidimensional curvature, which might result in missed local minima or maxima. Depending on the nature of the function that's being optimized, it may be possible to avoid the iterative process. The gradient creates a system of equations from the partial derivatives of the function. If each of the equations is set to equal 0, and one or more points satisfies that system of equations, then those points are the various minimums of the function. Knowing the points, the function can be evaluated to determine which is the global minimum. It should be noted that these methods discussed so far only work for continuous spaces, but the idea of making small moves iteratively through more optimal states can also be extended to discrete spaces. Now we're going to dive a little deeper into these ideas. If you'll recall from the review of linear algebra, a matrix can itself be considered as a function acting on a vector. For example, on the top here you can see an example of how you could generalize the output of a matrix to just refer to it as a function. The interesting thing is that, going off of this generality, you could think of a category of functions that take in a vector and return a vector, much like a matrix, but that can't strictly be written with matrix notation. This is shown in the example here. Since matrices are evaluated by taking the product of certain elements, a matrix couldn't encapsulate a function within itself for which the input was an argument, such as the trigonometric functions here. What's important to realize about this is that these new functions might be nonlinear, such as this one. This function is outside the domain of linear algebra, which was the focus of the review of the first chapter. While such a function might be nonlinear, it might be described as locally linear. This means that if you restrict your observation to a small enough area of the domain of the function, the output of the function might appear to be linear. I'm linking a video in the description which shows some really great visualizations and explanations of this concept. So in this framework, the question can still be posed: what are the derivatives of such a function? It's reasonable to ask how the output might change with a change in the input. The Jacobian matrix is the tool that describes this. It's a matrix with the partial derivative for every combination of subfunction making up the function of interest for every input variable. It's organized so that it has one column for each variable that has a partial derivative taken, and a row for each of the subfunctions making up the function for which the Jacobian is being taken. There's a link in the description to a video that explains how this works very well. On the screen here is an example using the function from the previous slide. The matrix the Jacobian creates happens to be squared because the input size is the same as the output size. The columns of the Jacobian matrix can be interpreted as vectors. Since the first column is the partial derivatives with respect to x, this column is a vector that points in the direction that the function is heading with an increment in the x component of the input. The output is a vector, and so the change in each dimension with respect to x needs to be considered to see the change in the output vector. So that's why the entire column of the Jacobian matrix could be considered. Alternatively, you could understand that the entire Jacobian matrix as representing the linear transformation that approximates the function, nonlinear function, in a small localized area for the point it's evaluated at. Earlier we looked at the gradient. The gradient is a function that acts on another function and returns all the first partial derivatives for that function. Keep in mind that the Jacobian and the gradient are not the same thing. The gradient returns a vector from a function, and the Jacobian function returns a matrix from a vector. They can't really be compared because of the different nature of their inputs and outputs, but you could see a similarity between the two, where each row of the Jacobian has the form of a gradient. Another important thing to note is that the partial derivatives inside the Jacobian are functions of x and y. It's this fact that indicates the solution space has some rate of change with respect to each variable, and that this rate of change is not constant. The fact that the rate of change is not constant indicates that the surface created by the function output in the domain is not characterized by straight edges and flat surfaces. Since the rate of change itself changes smoothly, this indicates that the surface has curvature. The rate of change of the rate of change is the definition of the second derivative of a function, and we get more information about it from the second derivative too. The Hessian matrix is a tool that provides information on all of the second derivatives of a function at a given point. The value in this is that because surfaces are more often curved than straight, the change in outcome resulting from a step of a given size in the direction of the gradient, the learning rate as seen previously, will not be equal to the actual change in the output. That's because on a curve, the directional derivative is tangential to the curve at the point. So the endpoint of that vector pointing in the tangent direction doesn't actually lie on the curve. This can be seen in the figure from the text. At a given point, the gradient yields the line of steepest descent, marked in green dashes. But for any learning rate, or step size, in the direction of that line, the subsequent point on the function does not lie on the green dotted line if there's any curvature. And there are subcases to this. With a negative curvature, the objective function decreases more than the gradient predicts. With positive curvature, such as on the right-hand side, the objective function decreases to a lesser degree than the gradient would predict. That is the information that the second derivative, and thus the Hessian matrix, provides. The Hessian matrix contains the second partial derivatives for every combination of two inputs for a function. If you recall, on the last slide, I mentioned that the gradient returns a vector from a function, and the Jacobian matrix returns a matrix from a vector. Conveniently, you can chain these two operations together as a shorthand for the Hessian matrix, as being the Jacobian of the gradient. This also provides another framework for intuitively understanding what the Hessian imparts, that being all the possible partial derivations of a set of function, in this case the slopes in various directions. Something to note about the Hessian matrix is that it's usually symmetrical. Specifically, it's symmetrical when the second partial derivatives are continuous functions. The authors specify that this is the case in most applications for deep learning. The reason it's symmetrical in those circumstances is because the order of the two partial derivatives being taken doesn't matter. It's commutative. The Hessian matrix can be used to compute the second derivative for a given function. It is equal to the direction vector transformed by the Hessian matrix and projected back onto itself. Since projection is equivalent to the dot product, this is equal to a single value, as one would expect based on the definition of the second derivative. The way I make sense of understanding this is as follows. As I demonstrated at length in my previous video on eigenoptimality, a symmetrical matrix will have orthogonal eigenvalues and vectors. If we decompose our direction matrix D into its eigencomponents relative to the Hessian matrix, then naturally the matrix transformation will increase the length of each component by its associated eigenvalue. Therefore, eigenvectors of different eigenvalues will be stretched to a different length. So it's only natural that the resulting vector wouldn't be in the same direction as the original vector before transformation. Projecting the transformed vector back onto the original vector can be understood to be necessary as the projection of the gain made by the transformation in different directions back onto the direction of interest. In other words, the unique eigenvalues of the Hessian matrix have their own characteristic values corresponding to the curvature in their direction. For a direction that is not collinear with an eigenvector, the curvature is a weighted sum of the different eigenvectors' curvatures, with more weight going towards those eigenvectors to which a vector is closest. As discussed in my video on eigenoptimality, an equation of this form will be maximized by a direction corresponding to the highest eigenvalued eigenvector of the Hessian matrix. As seen on the last slide, the second derivative will tell us how well we can expect the gradient descent step to perform. The second derivative indicates if the change in the objective function will be greater, less than, or equal to the size of the step taken. The Hessian matrix can be used to construct the second-order Taylor series approximation for the function we're looking at. The Taylor series is used to approximate a function by using its derivatives. This can be understood very simply by thinking of the case of a linear function, a line. For a straight line function, the derivative is constant, and so the derivative provides an exact match of the line if it's offset to be sitting on the line. In this way, the Taylor series could provide a perfect match for a linear function. That's because it takes a starting value, which is some point on the line, f at a, and then it adds to that the rate of change multiplied by the difference between the point of interest, x, and a. Taking this to a further case, we can imagine applying the same process to a parabola. Since it is curved, the derivative would not follow it perfectly, as we've seen before, and so there would be error introduced in the approximation. The idea of the Taylor series is that the error can be reduced if consideration is also given to the second derivative indicating curvature. In theory, the Taylor series is infinite, accounting for infinite derivatives, so we're making an approximation when we cut it off at some point for a multidimensional function. In this case, we have complete, perfect approximation with no error, cutting it off at the second derivative for a quadratic function. For higher order functions, we would have error, cutting it off at the second derivative. In the middle of the slide is what the second order Taylor series looks like using the Hessian. After expressing the updated point x as equal to the original point x, 0 plus some step in the direction of the gradient, the equation simplifies to the one below it. What's cool about this is that even expressed in this vector format to account for application to multivariate functions, you can see that the clear analog that this approximation represents in comparison to the basic kinematic equation used to compute a change in distance under some velocity and acceleration. The independent variable in this case is the change in position, or the step size, instead of the change in time. With this understanding, it's clear that the function is approximate, because using the physical analogy, it's as if we're computing the change in position with the assumption that the change in acceleration over time is 0. In the context of our multivariate function, we're assuming that the local shape of a function is a paraboloid. That assumption might work locally, but if that assumption or approximation doesn't apply globally, then that will lead to error that is proportional to the size of the step taken from a given point. There are a couple of more points worth noting. Consider the following in the context that the objective is minimization. Since the last term is positive, this indicates that a positive curvature in conjunction with a positive step works at odds to our objective, in terms of maximizing the change that results from taking a single step. Furthermore, for a sufficiently large step, the iteration will result in an increase to the function value if the last term is larger than the second. This is clear to understand imagining a 2D parabola. If you take a point on the left side and want to minimize, you move to the right. We're imagining a parabola that is curved upwards. But if you go very far to the right all at once, you may end up on the other side of the parabola, at a point higher than where you started. This is a natural byproduct of the positive curvature of the function. If the last term is 0 or a negative value, the Taylor series predicts that the function will decrease forever, so iteration would have no end. We know that that might not be the case though, because the Taylor function is an approximation. In practice, a heuristic should be used to select a step size. For a function with positive curvature, the optimal step size can be computed, as is seen on the bottom right. Naturally, our goal is to minimize the amount of computations necessary in reaching an optimum, and that's usually associated with taking larger steps. So it's good to understand why the least desirable situation of minimum step size occurs when the gradient is collinear with the largest eigenvalued eigenvector of h. Algebraically, it's the simple result that the gradient being the eigenvector maximizes the denominator. It can be understood visually by thinking of the parabola again. The greater the positive curvature of a parabola, the smaller of a step it takes to go to the minimum point, starting from a given height. If a parabola had less curvature and was very wide and shallow, then starting from the point x, where y was the same height as it was on the steep parabola, the x value would be much larger, and thus the step size to reach the minimum point would be 2. Critical point is known to be where the first derivative is 0. Building on this, the second derivative indicates if it's a local maximum, minimum, or a saddle point, if the second derivative is negative, positive, or 0 respectively. For a univariate case, the second derivative being 0 doesn't help to identify if the point is a saddle point or a flat region. This principle can be extended to multidimensional functions by looking at the eigenvalues of the Hessian matrix. The following statements are with respect to a point where the gradient is 0. If the eigenvalues of the Hessian are positive definite, the point is a local minimum. If the eigenvalues are negative definite, the point is a local maximum. In this multidimensional case, saddle points can be positively identified as points where at least one eigenvalue is positive and at least one eigenvalue is negative. This corresponds to the image on this slide. You can imagine taking a cross-section through the plane defined by x2 equals 0, and a 2D image formed by the cross-section would be a parabola opening upwards. Alternatively, a cross-section through the plane x1 equals 0 would have a parabola opening downwards. The last possible case is where all eigenvalues are of the same sign, but one or more equals 0. The type of point can't be concluded in the cross-section of the curvature corresponding to the direction of the associated eigenvectors. All this discussion about the second derivatives should make it clear that these are an important factor in determining which direction to explore while iterating to optimize. This is where the condition number of a matrix, which was introduced earlier in the slideshow, comes into play. If you recall, a condition number is the ratio between the largest and smallest eigennumbers of a matrix. In the context of the Hessian matrix, this number indicates the degree to which curvatures are different for a function along different axes. This image shows a function with a condition number 5. Interpreting the black ellipses as indicating height, like on a topographic map, you can see that the lines are much closer to each other along the axis that's diagonal from bottom left to top right, and much further on the axis from top left to bottom right. The implication then is that this is a function as a 3D surface. It would look like a long, narrow valley. The red line is showing a path taken by an iterative program using only gradient descent and using a computed optimal step size. It starts off at the topmost red point. It turns out that in a situation like this, the path of steepest descent points inwards towards the longitudinal axis of the valley, rather than towards the actual lowest point at the very center of the valley. You can understand that behavior by imagining letting a ball roll down a straight semicircular slide if you release it at the top of the semicircle at the top of the slide. It doesn't just track a straight line to the bottom and center of the slide. Instead, it rolls towards the center, oscillating. The same thing happens here. The result is that to our eye, knowing which direction is truly optimal, providing the shortest path to a minimum, the process results in a step going in the totally wrong direction. Continuing with this strategy, the step might overshoot that axis towards which it was aimed, and so the next step would then aim back at that axis, continuing downwards slowly. Cumulatively, this creates the long, winding path seen here, which is certainly many times longer than the actual straight line, most efficient pathway. This clearly provides the motivation to incorporate information from the Hessian matrix into the search. The means by which the information from the Hessian is used for optimization is through Newton's method. Essentially, computing the derivative and second derivative at a point, the function is then approximated as quadratic function, as we see here, and saw in the previous slide. If the objective function happens to truly be a positive definite quadratic function, then it only takes one step to optimize, as the derivative is computed and the point at which is equal is solved for. If it's not truly positive definite quadratic, then the fact that it's an approximation will result in the output being closer, but not right on the nearest minimum. This is assuming that the approximation function is convex. If the last term here is negative, we aren't completely lost. We know the function is converging to a saddle point. In that scenario, we can use gradient descent, without Hessian consideration, to travel across the surface away from the saddle point, and then go back to Hessian iteration once the curve is pointing to a real minimum instead of a saddle point. By reiterating through this process, the nearest minima can then be found much faster than by using the gradient alone. The equation to iterate with is shown at the bottom here. In general, optimization algorithms that use only the first derivative are called first-order optimization problems, or algorithms. Optimization algorithms that use the Hessian matrix are called second-order optimization algorithms. The authors note that in most contexts of the book, the optimization algorithms come with almost no guarantees, because the functions being optimized are so complicated. Restrictions or modifications can be made, though, to make some guarantees about a function. Lipschitz continuity is one of those. If a function is Lipschitz continuous, then it allows you to quantify the assumption that a small change in output to a function, such as a gradient step descent, will have a small change in the output. Beyond this, the authors note that the best suite of optimization techniques is available for convex functions. These are functions where the Hessian is positive semi-definite everywhere in the function. The reason is that these functions are well behaved, lacking saddle points. As a result, all their local minima are necessarily global minima. Unfortunately, it isn't every problem that can be expressed in such a way that the objective function to be minimized is convex. As such, convex optimization is only used as a subroutine for some deep learning algorithms. Due to the complexity of objective functions encountered in deep learning contexts, convex function optimization is greatly diminished. But some ideas from that field can be useful for proving convergence of deep learning algorithms. There are times when we want to maximize or minimize a function, but we can't accept optimizing inputs that are characterized by some criteria. In those cases, those criteria are constraints, defining the feasible solutions, and the problem is a constrained optimization problem. One common case in machine learning is to impose a norm constraint, such as is seen here. There are multiple ways these constraints can be imposed or handled mathematically. For example, gradient descent can be modified to fit a constraint by taking the computed optimal gradient and projecting it onto the set of feasible directions, yielding the optimum feasible solution. The more common methodology is the second listed here, which is to take a constrained problem and take a different perspective on it to define an unconstrained problem for which the optimal solution for the latter corresponds to that of the former. With an unconstrained problem in hand, any of the typical strategies can be used, making it easier. Sometimes it can be difficult to design the alternative problem and it takes creativity. An example is here. Say your constraint is that the resultant vector must have a norm of 1. The problem can be considered unconstrained by instead making the decision variable the angle theta, and defining the elements of the vector such that no matter the value of theta, the norm of the vector will equal 1. You can see how the redesigned problem would be unique and custom-made for each scenario with this kind of solution. Fortunately, the KARUSH-KUHN-TUCKER, or KKT, method provides a very generalized process for solving these types of problems. The KKT is a generalization of the Lagrangian method, which was touched upon in Chapter 2, Part 6. It generalizes the Lagrangian method in that it allows for imposing inequality constraints as well as equality constraints. The Lagrangian method is the method adding Lagrangian multipliers to an objective function to create the Lagrangian function. This modified function can be thought of as having an altered solution space, which no longer has the same curvature. The space is modified such that only those optimal solutions inside of the defined feasible region remain as optimal solutions. Other solutions that were optimal or infeasible are no longer characterized by a zero gradient. Thanks to this, we can just apply the other optimization methods to the Lagrangian function, knowing that it will not stop iterating at an optimal but infeasible solution. To do this, the set of all possible feasible solutions has to be defined by some bounds in the form of equality constraints and inequality constraints. Each one of these constraints gets its own unique Lagrangian multiplier, which are denoted lambda for the equality functions and alpha for the inequality functions in the expression at the bottom below. Basically, the old objective function simply has one new term added for each constraint, and each of those is multiplied by a coefficient, the Lagrangian multiplier. The expression at the bottom is the Lagrangian function, which is the new function to be optimized. As long as one feasible point exists and the function is not permitted to have value infinity, then the Lagrangian will provide the optimal point within the constraint region of the original objective function. As discussed previously, if maximization is desired, then the generalized Lagrange function of the negative of the objective function can be taken. Adding the negative sign changes the outcome of optimization from minimization to maximization, even while the process itself is still minimizing. It's possible to have more of a deeper understanding regarding the value that the constraint functions take on. At a feasible point where the constraint function of the inequality type is less than 0 as opposed to equal 0, that constraint is said to be inactive. This can be understood as indicating that the constraint is not on the cusp of being violated. Since these constraint functions take on a negative value at a local optimal point where they're inactive, and the function is being maximized with respect to their coefficients, the set of alphas, the alpha for the inactive constraint, will be 0 to take that negative out of the maximization. It's also the case that at least one of the inequality constraints will always be active for any solution. This information lays the groundwork for the conditions which must be true for a given point to be optimal when implementing the KKT theorem. There's a link in the description to a video that nicely explains the third condition. Finally, the chapter is rounded off with an example of the application of optimization techniques to the classic linear least squares problem. The objective is to determine what line best fits a set of data points. For a refresher on the premise of the matrix interpretation of this problem, there's a great video linked in the description. As was discussed in this chapter, we can simply add the gradient, apply the gradient to determine in what direction a step should be taken. The symbolic computation of the gradient allows us to compute it at any point in the space, so that's strong, and allows the creation of a very simple algorithm. Given the infinitesimal nature of continuous space and the step size that we choose to select, there's practically no chance that the iterative process of stepping in the best direction will ever reach the true optimal point. Therefore, we select a threshold which defines a limit. That's the satisfactory limit at which point the iterative search will end. It's selected based on the norm of the gradient vector. That's a good choice because we know the gradient will be the zero vector at the optimal point. So we can use the difference between a given gradient and the zero vector to define the limit without knowing where the point that it will be zero at actually is. Having computed the gradient and the tolerance, the algorithm encapsulating the search for the solution is captured inside of a single piece of loop logic. We can look at other methods as well, such as Newton's method. Since the subjective function is quadratic, the quadratic function approximation created by Newton's method is exact, so the optimal solution is reached in a single step. Alternatively, we learned in Chapter 1 that the Moore-Penrose pseudo-inverse using singular value decomposition could be used to solve this problem and provide the optimal vector. But what if the problem was constrained? If optimal vector were limited to a feasible space, and the true optimum was outside of that space, the pseudo-inverse wouldn't be able to find it. We can try to solve for that scenario as well, using the Lagrangian method. A constraint we can impose is that the norm of a vector, x, is equal to 1. Essentially, this means the solution space is constrained to the unit circle around the origin. First, the Lagrangian function is created. Then the gradient with respect to x is taken. Setting it equal to 0, this creates a symbolic expression for the condition under which our decision is optimized. The vector x can be isolated from this function. This would give us the solution, if not for the fact that lambda is unknown at this point. What we then do is perform gradient ascent with respect to lambda to determine what kind of steps it should take, and that's because we are maximizing with respect to lambda. It's clear that when the norm of x is greater than 1, the derivative of the Lagrangian is positive. Therefore, lambda takes a positive step. Lambda increases. Thinking back to our original function where the Lagrangian multiplier is added to the function, the result is that the lambda increasing means that our objective function is larger, which was at odds with our objective to minimize it. What makes this work is that when x is recomputed with a larger lambda value, x gets smaller, bringing its norm nearer to 1. This iterative process is what brings the norm of x to be 1, and eventually yields the optimal constrained solution. And with that, Chapter 4 is complete. The next video will be moving on to Chapter 5, covering machine learning basics. Thanks for watching and take care.